Hello everyone, welcome back to my channel Study With Me. Today I'm going to explain about Chemistry Higher Level Paper 2, May 2023, Time Zone 2. If you find this video is helpful, don't forget to subscribe and let's get started. Analytical and spectroscopic techniques enable chemists to identify and determine structures of compound. An unknown organic compound X, comprising of only carbon, hydrogen, and oxygen, was found to contain 48.6% of carbon and 43.2% of oxygen. Therefore, the percentage for oxygen, we just need to subtract from here. So carbon is 48.6 and oxygen is 43.2. So 100 minus 48.6 and 43.2, it will be hydrogen, so 8.2. So we need to find mole for each of this element. For carbon, 48 divided by 12.41, that would be 4.05 mole. And for oxygen, that would be 43.2 divided by 16, that would be 2.7 mole. And for hydrogen, that would be 8.2 divided by 1.01, it's 8.12. So to determine the empirical formula, we divide the number with the smallest number among these three, which is 2.7. So we'll get for C 4.05 divided by 2.7 would be 1.5, and for oxygen will be 1, and for H will be 3. So we cannot write C 1.5, so we times multiple 2 for all of this. That would be C 3, H 6, and O 2. Alright, so for the next question, I cannot really explain because the picture is removed for copyright reason, but we really need the answer for this question. So I look at to the IBMAR scheme. The MZ74 is C3H6O2 plus, and for 45 it will be COOH plus or C2H5O plus. So something that I can explain here, why 74 is C3H6O2. If you calculate the molar mass of C3H6O2, that would be 74. The same goes to COOH. So 12 plus 16 plus 16 plus 1, that would be 45, or C2H5O, also that would be 45. But usually the compound itself, it gives the highest number, so most probably and high possibility the compound would be C3H6O2. Okay, so this is related to the next question. So C3H6O2 or COOH, so there's COOH right there. Therefore, there is functional group right here. So it's 3000. If you look at to the data booklet, section 26, as you can see here, for OH is between 2500 to 3000. So for this peak is 3000, so it's OH, and another peak is around 1700 something, so it's aldehyde or C double bond O, aldehyde ketones, carboxylic acid, and ester, so between 1700 to 1750. So this is C double bond O. So the answer for this question is OH and C double bond O. Okay, next, deduce the structural formula of X. So as we have MZ74 and 45, which is COO, which is from the previous question. So, and also C2H5O plus, that would be 45 as well, these two. And most definitely the compound is this C3H6O2, and it has COOH. It means carboxylic acid. So if we deduce the formula, that will be CH3 CH2 COOH. Okay, so for CH3H6O2, so that would be the whole thing except H. And for COOH, this will be COOH. And C2H5O, that will be from here until here. Oh, okay, so exclude another C here. So C2, H5, and O. So as in the ER, it shows C double bond O and then OH. So that's why it's mostly carboxylic acid. Okay, so 0.363 gram of organic liquid Y was vaporized completely at 95 degrees Celsius and 100 kilopascal. The gas volume was measured to be 81 centimeter cube. Determine the molar mass of Y. So it's PV and RT, and M divided by MR RT. So if we rewrite the equation, MR will be M times R times T divided by PV. So that would be 0.363 times 8.31 times 368, because 95 degrees Celsius we convert it to be Kelvin, and divided by pressure. Pressure is 100 kilopascal times 0.0810. Okay, if pressure is Pascal, volume should be meter cube. If pressure is kilopascal, the volume should be decimeter cube. So we convert centimeter cube to decimeter cube, and you will get 137047, and so comma 047. So the MR is 137. Okay. Nitrogen 4 oxide, NO2, is a brown gas found in photochemical smoke and has a pollutant causing acid deposition. Nitrogen 4 oxide exists in equilibrium with dinitrogen tetroxide, N2O4, which is colorless. At 100 degrees Celsius, Kc for this reaction is 0.0665. Outline why this indicates about the extent of this reaction. Okay, Kc here, it's smaller than 1. So having Kc smaller than 1, making reaction hardly to proceed. Or it is reverse reaction. So if it's reverse reaction, it means concentration of reactant, it's bigger than concentration of product. The other way around, if it's Kc bigger than 1, the reaction proceeds almost all towards reactant. Okay, so that's the difference if it's Kc smaller than 1 or Kc bigger than 1. Calculate the Gibbs free energy change delta G for this equilibrium at 100 degrees Celsius. Use section 1 and 2 of the data booklet. Mostly it's about the number of R and formula. So delta G is RT ln K. So negative 8.31 times 363, because the temperature is 100 degrees Celsius, in Kelvin is 363, and 0.0665 comes from this number. So you will get 8.40 kilojoule per mole. Calculate the value of Kc at 100 degrees Celsius for the equilibrium. If you compare with the first equation, is actually reverse. So N2O4 now becomes reactant. So Kc will be Kc to the power negative 1. So 1 over 0.0665, that would be 15. Okay, if reverse, the Kc to the power negative 1. If it's half of the coefficient, that would be square root of Kc. If it's double the coefficient, that would be Kc squared. Okay. Calculate the standard enthalpy change in kilojoule per mole for the reaction N2O4 produce 2N2. Okay, to calculate the enthalpy change of this will be delta HF product minus reactant. So that would be 2 times 33.18, because the coefficient is 2, minus 9.16, which is 57.20 kilojoule per mole. Calculate the standard entropy change in joule per mole. So delta S will be delta S product minus reactant. Okay, so product again 2 NO2, 2 times 240.06 minus 304.29, that would be plus 175.83 joule per mole. Okay, deduce the Lewis structure of N2O4. N2O4. So just what the bond length indicate about the structure of N2O4. You see that it has resonance. So it means based on equal NO bond length is 1.19 times 10 to the power negative 10, because it said are all. So resonance structure often involve the localized electron. This implies that the bonding between nitrogen and oxygen atom is equivalent throughout the molecule, because it has resonance structure. Predict O and N bond angle in N2O4. So when you go back right here, O and N. So let me just copying it down again, the structure. Okay, so this is trigonal planar. So if it's trigonal planar, the angle will be 120 degrees. Acid deposition is formed when nitrogen oxides dissolve in water. Write an equation for nitrogen 4 oxide reacting with water to produce two acids. So it's 2NO2 gas react with water in liquid state, producing HNO2 aqueous state and HNO3 in aqueous state as well. Okay, so an electrolytic cell was set up using inert electrodes and dilute aqueous solution of magnesium chloride, MgCl2. Annotate the diagram to show the movement of particles that conduct electricity in this cell. Okay, so we have MgCl2 that would be dissolved in the water. So the ion here will be Mg2 plus and H plus, also Cl minus and OH minus. So definitely is a positive. So Cl minus will be here and OH minus will be here as well, both of them. And then we have Mg2 plus and H plus, that would be negative electrode. Okay, so this will be anode, this will be cathode, because for me, panic. So positive anode, negative cathode, and an ox cath red. So cathode will experience reduction and anode will experience oxidation. So oxidation, losing electron, and reduction, gaining electron. Okay, so annotate the diagram to show the movement of the particles that conduct electricity. So these annotate, we already annotate them. And the second one, deduce the half equation for the reaction at each electrode. So positive electrode, as we can see here, positive electrode, we have OH minus and Cl minus. So if we look at to the data booklet, section 24, okay, so we have, okay, let me make it better. Okay, so we have OH minus. So OH minus losing electron here. So well, let's find that losing electron for OH minus. Okay, here. But here is gaining electron. So we need to flip the reaction because losing electron. So that would be 2 OH minus aqueous producing half O2 gas plus H2O liquid plus 2 electron. And for negative electrode, we have H plus. So it's gaining electron because experience reduction. So H plus plus electron producing H2. This will be 2 here and this will be 2 electron. Okay. So graphite rods are sometimes used as inert electrodes. Describe the structure of graphite and explain why graphite conducts electricity. Layer of carbon atoms in a giant structure, because graphite is one of the compound that has giant structure. It conducts electricity as it has delocalized electron that flows along layers. Okay, graphite consists of layers of carbon that is arranged in a hexagonal lattice structure. Each carbon atom is bonded to other 3 carbon atoms, forming strong covalent bond within layers. Within each layer of graphite, 1 electron from each carbon atom is delocalized, facilitating the flow of electric current, allowing to conduct electricity effectively. Okay, next question is Winkler titration can be used to determine the biochemical oxygen demand BOD of a water sample. One set of equations for the reaction occurring below. Okay, so this is our target. Okay, the Winkler method is used to determine concentration of dissolved oxygen in water. Oxygen first oxidize the soluble Mn2 plus to form insoluble manganese hydroxide. Okay, that will react with I minus here, with I minus and H plus, forming I2. The form I2 then reacts with excess I minus, forming I3, ion I3. Okay, I3 minus then is titrated with thiosulfide ion. Okay, that would be used to determine the amount of dissolved oxygen. Okay, because when I3 minus is titrated with thiosulfate, it is proportional with the concentration of oxygen. So this is to measure measuring volume of thiosulfate ion can help to calculate dissolved oxygen. So determine the concentration in mole decimeter cube oxygen dissolved in the water sample. So the volume is 0.15 decimeter cube, and so 36.0 centimeter cube of thiosulfate is used with the concentration is 0.005. So this will be 0.036 decimeter cube. So the first one, what do we do? It's to calculate mole of thiosulfate ion, that would be 0.05. So to calculate mole, mass times concentration, which is 0.05 times 0.03, you will get 1.8 times 10 to the power negative 4 mole. Okay, then you can calculate mole of I2 because it's we go up here until we reach oxygen. So mole of I2 will be half of mole of thiosulfate because thiosulfate here is 2. So half times 1.8 times 10 to the power negative 4, that will be 0.0009 mole. And then we find mole of Mn2 plus. So I2 and Mn2 plus, okay, it's the same. Okay, I2 and Mn2 plus, they have the same coefficient, so that will be the same number of mole because it will be 0.0009. And next, mole of Mn2 plus, okay, with MnOH. Okay, so in this reaction, MnOH2 and Mn2 plus, they are the same. Even here, the coefficient are the same. So with mole MnOH2, also 0.009. Okay, then next for oxygen, okay, for oxygen here, we see that the coefficient is 1 and here is 2. So it's half of mole MnOH2. That would be 0.00045 mole. So to find the concentration of O2 will be 4.5 times 10 to the power negative 5, this one, divided by volume, which is 0.15, and you will get 3 times 10 to the power negative 4 mole per decimeter cube. So 0.15 is coming from water sample, volume of water sample. Okay, outline how the BOD of the water sample could be determined. So you can do titrate. So this to measure dissolved oxygen in water sample. So the difference between two values represent BOD. Okay, to determine BOD of water sample, dissolved oxygen is measured right after water or sample is collected. Then it is stored for 5 days to allow microorganisms in the sample to consume organic matter. Then dissolved oxygen again is measured. So you will have the first dissolved oxygen and then the second dissolved oxygen. The difference between the first and the second dissolved oxygen will represent BOD, because it means the amount that is consumed by the microorganism. So suggest what a low BOD value indicates about a water sample. It means not a lot of microorganisms consume DO. So the answer will be low levels of oxygen consuming of water pollution. Okay, because low DO difference and low BOD. The periodic table provides information about electron configuration and physical and chemical properties of elements. Bismuth has atomic number 83. Deduce two pieces of information about the electron configuration of bismuth. Okay, bismuth 83. And if we see the periodic table for bismuth. Okay, so it's period 6 and group 15. So Bi has 5 valence electron, as it is in group 15, and also occupied D or F orbitals. So D obviously because it's on the non-metal side. So here is even to non-metal sides, here is S and then this D and then P, but the atomic number is very high, so of course it will reach D and F orbitals because it has a lot number of electrons. And if we look at here, it will start with 6s1, 6s2, 6d1 again until 6p1, 6p2, and then 6p3. So if p3, so it has unpaired electron. You can choose 2 from this 3 unpaired electron. Okay, outline why aluminum is malleable. Malleable means easily to be bent or hammered into shape. So layers of cations slide over one another without disrupting bonding, or even though we hammer the metal because it's malleable, so changing shape does not disturb the bonding. Okay, so metal has a lattice structure. So example, this is one layer, another layer, and another layer. So this regular structure means that the different layer can slide over one another. So this layer can slide over one another here. So they are not as fixed as you might thought. All right. So the next, an 11.98 gram block of pure aluminum was heated. Calculate the heat energy absorbed in joule to increase its temperature from 18 to 40. The specific heat capacity of aluminum is 0.902. So it will be Q MC delta T. It's 11.98 gram times specific heat capacity, which is 0.902, times difference in temperature. You will get 238 joule. Okay, so next question. Argon has 3 naturally occurring isotopes, which is AR36, AR38, and AR40. Identify the technique used to determine the relative proportion of the isotope. Only mass spectrometry, or you can also say mass spectroscopy. Okay? Mass spectrometry is to identify and characterize chemical compounds based on the mass to charge ratio of their ion. Calculate the relative atomic mass of this sample, giving your answer to 2 decimal places. So to calculate AR, that would be 0.0034. So I directly divided by 100 times 36 plus 0.0006 times 38 plus 0.996 times 40, you will get 39.99. Okay, next question. Methanoic acid is a monoprotic weak acid. The concentration of methanoic acid was found by titration is 0.2 molar standard solution of sodium hydroxide using an indicator to determine the endpoint. Calculate the pH of the sodium hydroxide solution. So it's titrated by NaOH and the concentration is 0.2. So concentration of OH minus is 0.2 mole per decimeter cube. So POH will be negative log 0.2, which is 0.9699. So pH will be 14 minus 0.699. You will get 13.301. Write an equation for the reaction of methanoic acid with sodium hydroxide. So HCOOH aqueous plus NaOH aqueous. Okay, if you struggle to write down the product, you can just make it into ion. So HCOO minus and H plus because it's acid, and then Na plus OH minus. So HCOO minus will pair with Na plus because it's negative and positive. So that would be HCOO Na aqueous, and we have H plus OH minus, of course, will be H2O liquid. Okay, 22.5 centimeter cube of NaOH neutralize 25 centimeter cube of methanoic acid. Determine the concentration of the methanoic acid. So volume of NaOH is 22.5 centimeter cube, and methanoic acid is 25 centimeter cube. So as per equation, 2 N acid, the same with an OH minus, mole acid, the same with mole OH minus. So concentration of the acid will be 22.5 centimeter cube divided by 25 centimeter cube times 0.2 mole decimeter cube. So this will be finished, and you get 0.18 mole per decimeter cube. Calculate the pH of the original solution of methanoic acid. Use your answer 2A3 and section 21 of the data booklet. Okay, so methanoic acid, section 21, it's about Ka. Section 21. Okay, so it's Ka of methanoic acid. Okay, so it's 3.75. All right, so Ka is 10 to the power pKa. That would be 1.78 times 10 to the power negative 4. So H plus is Ka times molar. So 1.78 times 10 to the power negative 4 times 0.18. You will get 5.66 times 10 to the power negative 3 for H plus, concentration of H plus. And pH will be negative log 5.66 times 10 to the power negative 3, 2.247. So 0.18 is coming from this concentration. If you don't get it, you can use 0.3. Identify, giving a reason, a suitable indicator for this titration. Use section 22. Okay, pH is 2.247 and we use NaOH. So it's between titrations between acid and strong base, which is NaOH. So the pH, because methanoic acid is a weak acid and is titrated using NaOH, which is strong base, so the pH definitely will be bigger than 7. So if pH bigger than 7, the indicator will be phenolphthalein, PP. So that will be the indicator. Therefore, the answer will be this: color change in the pH range of equivalence point from colorless to pink. Okay, weak acid versus strong base, pH bigger than 7. Write an ionic equation to show why a solution sodium methanoate does not have pH of 7. Plus H2O, it's liquid, and then produce HCOOH aqueous and OH minus aqueous. Okay, the original when HCOONA, sodium methanoate, is dissolved in water, it dissociates into its ion. So the original reaction, actually HCOONA solid produce HCOO minus aqueous plus Na plus aqueous. Okay, then HCOO minus reacts with water, producing this equation. This produce HCOOH and OH minus. So this acid is a weak acid, partially produce H plus in aqueous solution, but we have OH minus. OH minus cause pH becomes greater than 7 as it is ion of a strong base. That's why pH, it doesn't have a pH of 7, but it's greater than 7. Bromine, Br2, and methanoic acid react in the presence of sulfuric acid. Suggest an experimental method that could be used to determine the rate of reaction. To determine the rate of reaction, you can always measure change in mass or in pressure or in volume of gas CO2 produce, or you can also check electrical conductivity. The sulfuric acid is a catalyst in this reaction. How a catalyst increases the rate of reaction. Catalyst provides an alternative pathway, reaction pathway, and lowers the activation energy. Methanoic acid can react with ethanol to produce ester. As you know, when alcohol plus carboxylic acid, it will produce ester and water with the catalyst concentrated H2SO4 and heat. So when it's ethanol, so here is ethanol plus methanoic acid, it will produce ester, which is alkoxy alkanoate. So the reaction, I will make it here so it will be clear for you. So ethanol OH plus methanoic acid OH. So this H will be eliminated. So this O will bond with this C, all right? And then OH also, this will be eliminated. So it will produce the formula, which is CH3 comes from ethanol, and C, that would be bonded with O, so CO and C from here, double bond O and H. Okay, so alkoxy alkanoate. So alkyl, sorry, it's not alkoxy alkanoate, but alkyl alkanoate. Okay, alkyl. So we have two here. So it's ethyl methanoate, because it's only one C here, methanoate. All right. Next, predict the number of phenol and their splitting pattern in the HNMR spectrum. Okay, so let me write it down back, the formula. So Lewis structure, CH3, CH2, and OCOH. So number of phenol will be 3 because it has first 1 H environment. So there are 3 environment of proton, 1, and then CH2, and then CH3. So it will be 3 phenols. And splitting pattern, you know, singlet next door carbon, no H attached. Okay, so this will be singlet. Okay, let me just write down here. And for CH2, okay, next door to carbon CH2, so this will be triplet because it's next door to CH2. And next door to CH3 will be quadruplet. Okay, for doublet next to CH group, there is no CH group, so that's why there is no doublet. State one reason why tetramethylsilane TMS is often chosen as an internal reference standard for the calibration of HNMR spectroscopy, because it's singlet and no splitting pattern, and inert or stable, and also soluble in most organic solvent. Write the equation for the complete combustion of ethanol. Ethanol C2H5OH. So complete combustion react with oxygen. If it's complete, producing CO2 and H2O. If it's incomplete, produce carbon monoxide, CO. So this will be 3, this will be 2, and this will be 3. Don't forget to balance the equation. Determine the enthalpy change for the combustion of ethanol in kilojoule per mole. Okay, so the structure will be CH. I really like to always write down the structure, so I will not make a mistake when calculating how many C bond to H or C and C, something like that. Okay, so it will be clear. Otherwise, you tend to make mistake. So 2CO2 plus 3OH. So we can see here we have 1CC and then 5C, so plus 5CH and plus 1OH plus 3O double bond O. So 4CO plus OH, there are 2 here, so 3 times 2, so 6OH. So based on the average bond enthalpy in the data booklet, you will have the number 346 plus 5 times 414 plus 358 plus 3 times 498. 4 times 804 plus 6 times 463. The total will be 4731, and this one is 5994. So delta H will be bond forming minus bond breaking. So 4731 minus 5994 will be negative 12633 kilojoule per mole. Okay. Hydrogen bromide HBr reacts with but1-ene. Identify the type of reaction. It will be electrophilic addition, because butene, so alkene, double bond, so HBr will be added into the butene. Okay, it's electrophilic because HBr is acting as an electrophile. Electrophile is a reagent that accepts a pair of electrons to form covalent bond. And but1-ene is acting as a nucleophile because it has pi bond. 2 products are possible. Explain the mechanism for the formation of the major product using curly arrows to indicate the movement of electron pairs. Okay, so but-ene so here will be H, here will be H, react with HBr. Okay, so the curly arrow will be here and Br will leave. I will explain this later. So let me just write the structure first. So this will be positive, and Br, it will go right here. Okay, so it's only 2 CH2 CH3. So the final product will be CH3 and CH, so Br will be here, and C2H5. Okay, so electrophile is it's a positive charge molecule, or partially positive or neutral, which is in this case will be HBr. So nucleophile, butene, attacks, so the pi bond here, okay, attacks electrophile, cause the double bond breaks, forming carbocation, the C plus. So carbocation, which is positively charged and accept a pair of electron from the Br ion, and forming 2-bromobutane. All right. Explain why the mechanism result in one product being formed in greater quantities than the other. So it's because secondary carbocation with ethyl group is stabilized. It's more stable than primary carbocation. Also, the reason is greater inductive effect on secondary carbocation. Okay, so secondary carbocation is more stable because it has more adjacent carbon atom spreading out the positive charge. So this carbon atom, it's directly bonded to another carbon atom in molecule. So carbocation, if we want to compare the primary carbocation with secondary and tertiary, why it is more stable, I will just draw it here so you can see the primary carbocation. So this is the inductive effect. So this for primary carbocation, and then for secondary it will be 2CH3, so 2 more effect, and then for tertiary it will be 3 of them. Okay, so it has more alkyl attached, exerting a stronger electron donating inductive effect, further stabilizing the positive charge. So inductive effect, influence of nearby atoms of groups on the electron density of a molecule like donating electron. So it will affect stability and reactivity. So that's why secondary carbocation with ethyl group is more stable than primary carbocation. As you can see, this one, it's secondary carbocation. Draw the structure of a section of a polymer formed from 3 monomers of but1-ene. So for but1-ene is CH2, CH, and CH2, CH3. I will say C2H5. So CH here is double bond, and CH, so we have CH2 here, okay, and don't forget the bracket, and then CH, so it's not double bond anymore, and C2H5, so CH and then here C2H5. So it's 3 monomer, so we just repeat 2 more time. And don't forget N. Deduce the hybridization of the first 2 carbon atoms in butene. So butene, this is the first 2 carbon, okay? So this will be both sp2. You see, sp2, sp2. Describe the bonding between the first 2 carbon atoms in but1ene in terms of orbitals of this atom. So sp2, because the orbital sp2, mixing of s and 2p orbital, s it's sp2, and for sp2 it's head on, and n to n overlap for sp2, or pi bond. You know pi bond is an overlap p orbital above and below internuclear axis. That it's the case for every pi bond. All right. One isomer of C4H9Br can exist as stereoisomers. Draw the 3-dimensional structure of the 2 stereoisomers using wedge dash notation, clearly showing the relationship between them. So C4H9Br, it will be, let me make it a bit nicer. So this will be H, and this will be Br, and this CH3, and this C2H5. So it's stereoisomers, okay? So it's the mirror, that would be the opposite, CH3. So that would be like this, Br, and C2H5. So it's a line in a plane of paper, and this dark wedge projects towards you, and this one is dash wedge projects away from you. Solid ionic compounds from crystal lattice. Enthalpies of solution, hydration, and lattice enthalpy are related in an energy cycle. Annotate the energy cycle for the enthalpy of solution of solid magnesium chloride by naming the process. So MgCl through enthalpy of solution, okay, enthalpy of solution will produce Mg2 plus aqueous and 2Cl minus aqueous. And through lattice enthalpy, process B, lattice enthalpy, will produce Mg2 plus gaseous atom and 2Cl minus gaseous atom. And these two, through enthalpy hydration, okay, will produce Mg2 plus aqueous and 2Cl minus aqueous. So what is enthalpy solution? Is when ionic compound dissolve completely in water, so it will be ions in aqueous state. That's why it's enthalpy of solution. So it will be dissolved in a solvent, so that's why it will be both aqueous. And for lattice enthalpy, breaking apart the solid compound into gaseous atom, so that's why B process is a lattice enthalpy. And the second stage after lattice enthalpy is enthalpy hydration. So the gaseous atom will be surrounded by water molecule, so it will be aqueous again. So this is direct and this is indirect process. Okay. Calculate the enthalpy of solution for magnesium chloride MgCl. Use section 18 and 20 of the data booklet. Enthalpy of solution is enthalpy, lattice enthalpy, plus hydration enthalpy. So lattice enthalpy plus hydration of Mg2 plus and 2 hydration of Cl minus. So section 18 and 20. So 20, we need hydration of Cl minus. So there is Cl minus here, and then Mg2 plus right here. Okay, and lattice enthalpy of MgCl2 is right here. So we can just plot into the formula 2540 minus 1963 plus 2 negative 359. You will get negative 141 kilojoule per mole. Explain why the lattice enthalpy of barium chloride BaCl2 is lower than that of magnesium chloride. Okay, so ionic radius of Ba2 plus, ionic radius of Ba2 plus is greater than that Mg2 plus. It causes weaker attraction between Ba2 plus and Cl minus ions. Okay, Ba is in period 6, so it has more shells, therefore bigger radius and bigger ionic radius. But Mg is in period 3. As the ionic radius increases, lattice enthalpy also decreases. This is because larger ions have weaker attractive forces between them, resulting in lower lattice enthalpy. As you remember, lattice enthalpy is the energy required to break apart solid compounds into gaseous atom. Because of the ionic radius increases, the attractive forces also decreases, so it's easier to break them apart. Cobalt also forms chlorides with the formula COCl2. State full electron configuration, the cobalt 2 ion. If it's cobalt only with the number 27, that will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d7. But for cobalt 2 plus 27, so we need to remove 2 electrons from S, so it will be Ar. Okay, I make it short, 3d7. Hydrated cobalt 2 ions, COH2O62 plus, are pink. Describe the interaction between the cobalt ion and a water molecule in terms of type of bond and how this bond is formed. So it will be coordinate bond, or what we call dative bond, and water is acting as the ligand that donates pair of electrons to cobalt to iron. Okay, coordinate covalent bond are formed between the ligand and the transition metal ion. So in this case is H2 is the ligand and then CO as a transition metal ion. This involves the ligand donating electron into the empty 4d and 4s orbital cation, at least for the first row of transition elements, not the partially occupied 3d orbital. COCl4 two ions are blue. Explain why the different ligands cause different colored complex. It's because of magnitude as of energy gap between split d orbitals differs depending on the ligand, and also the energy gap determines the wavelength of light absorbed or color. Okay, different ligand cause different colored complex because they affect magnitude of the energy gap between split d orbitals. In the d orbitals, we have 5 orbitals, so it will be split 2 and 3 orbitals in the central ion. This energy gap determines the wavelength of light absorbed by the complex, leading to its specific color. Essentially, the energy absorbed by the electrons to transition to higher energy levels corresponds to different wavelengths of light, resulting in different colors for complex formed with different ligand. The last one, the initial rate reaction was determined for the reaction between bromide ions and bromide ions, BrO3- in acidic solution. So these are the concentration and initial rate. So to find out the order, we have 3 order: 0 order, first order, and second order. So 0 order, when you change the concentration, it doesn't affect the rate doubling the reaction. First order, when you double the concentration of reactant, would double the rate as well. Second order, double the concentration of reactant, quadruple the rate. Okay, we'll see for the experiment 1 and 2 for H+. Okay, 1 and 2. So this one the same, and this one the same, and this one. So doubling the concentration would double the rate. This is not double, but quadruple. Okay, so it will be second order. And for the experiment 2 and 3 for BrO3-, 2 and 3, so this one the same, and then this one the same, and this one. So double the concentration will double the rate. So it's first order. And for the experiment 1 and 5 for Br-, 1 and 5, so this is the same and this is not. Okay, so Br-, and then this the same. So you see, double the concentration, double the initial rate. So this is first order. So the rate will be K, BrO3- and Br-, and H+ squared. The rate of a reaction at 50 degrees Celsius is 3 times the rate at 25 degrees Celsius. Calculate the activation energy in kilojoule per mole for this reaction using section 1 and 2 of the data booklet. Basically is the formula. So ln K1 K2 equal to EA divided by R 1 over T2 1 over T1. So because it's 3 times, so it would be 1 over 3 EA 8.31 1 over 3 to 3 because it's 50 degrees Celsius and 1 over 298. We can rewrite the equation will be EA equal ln 1 over 3 times 8.31 divided by 1 over 323 minus 1 over 298. And when you do the calculation, you will get 35.1 kilojoule per mole. All right, so that's all for the explanation paper 2, HL May 2023, time zone 2. I hope it will be helpful for you. And don't forget to subscribe to my channel and also let your friend know so you guys can study together. And bye for now.